Our last lesson was on Lewis structures, and so today what I want to talk to you about is resonance and the concept of resonance. Resonance occurs when you have equivalent Lewis structures, but on paper they look like they're different. So we're going to talk about that. This is a Lewis structure for ozone. If you were to draw the Lewis structure for ozone, this is his Lewis structure. And notice you have a single bond here and a double bond here. Well, you could just as easily have drawn the double bond on the opposite side and the single bond on the other side. So that structure that I just showed you on the other slide is at odds with what the true observed structure for ozone is. Because if you look at the observed structure, if you measure the bond angle here, it's not quite 120 for bent, but it's close to it. But the bond length is what I'm thinking of now. The bond length is 1.278 angstroms in both cases. These are equal bond lengths, which is opposed to what we saw with this one, because there's a single bond, there's a double bond. So we know single bonds are longer than double bonds. So you want to think of resonance sort of like when you're mixing colors. Just as green is a mixing or a synthesis of blue and yellow, so yellow and blue make green. Resonance is a mixing of your Lewis structures to get the ozone molecule, which is somewhere in between. It's like a mixing of the two. So these are both equivalent, and so what we do to indicate the situation of resonance is we draw an arrow between the structures, just like this, pointing in both directions. Ozone is an average or a mixing of these two resonance structures. So when more than one valid Lewis structure can be drawn, we use resonance structures to describe the molecule. The actual structure is an average of the two resonance structures that we just saw. So the bond lengths of this in the structure are going to be identical to one another and will be between those of a single and double bond. If you consider these two equivalent Lewis structures for HCO2, notice that the carbon, when you draw the structure, had to borrow some electrons to fill his octet. So he had a choice of either of these two oxygens to borrow from or to get to pull some to him through his electronegativity. So he could pull from this oxygen on the right or from the one below. So you'll notice I draw both structures. Here the double bond is between the oxygen on the right, and here the double bond is on the bottom oxygen. These are equivalent, and so we would draw both, and we have the arrow in between indicating resonance. Because in truth, the electrons that form the second CO bond, the double bond we see here, it does not always sit between the carbon and the oxygen. It's not static like we see here. This is kind of like a picture at a moment in time, and this is a picture at another moment in time. The electron is moving. It's called delocalized. It's not localized. And the electrons move among the two oxygens and the carbon. They are not localized, but as I said, they are delocalized. So you kind of think of them as they're moving among these back and forth. It's not a true double bond. It's not a true single bond. It's sort of like a 1.5 if you want to think of it that way. It's an average of the two. So how does resonance tie into bond length and bond energy? Well, resonance bonds are shorter and stronger than single bonds, but they are longer and weaker than double bonds. As I said, they're somewhere in between. So I want you to practice drawing a resonance structure for the nitrite ion. Pause the video and then pick up and check your answer. I'm going to go ahead and draw mine because I'm short on time with my video here. It's going to cut me off, I'm afraid. So add up your valence electrons. Nitrogen has 5 valence electrons, plus the oxygens have 6 apiece because they're in group 6A. There's 2 oxygens. And the -1 charge means that it has gained an electron. So you add an additional electron. That gives you 5 plus 12 plus 1, which is a total of 18 total electrons to bond with. So when you start setting up your Lewis structure, you have your nitrogen in the center and you put your oxygens on either side, keeping it symmetrical. So that's 4 electrons that we've used so far. So I'm going to come over and subtract. That means I have 14 electrons or lone pairs to place out. So I start placing the electrons in pairs: 2, 4, 6, 8, 10, 12, 14. So there's the 14 that I had. So I've run out of electrons. I have no more. And as you check, the oxygens do have their octet rule satisfied. But if you consider the nitrogen, he has 2, 4, 6. So he is not satisfied. So he can borrow from this oxygen or this oxygen. So one of the structures you're going to draw is going to have a double bond on this side. So I'm going to redraw it over here. And remember, your Lewis structures, if they're for polyatomic ions, should always be in brackets. So I have a double bond here, nitrogen and a single bond, and then your oxygen. And you're going to place the electrons 2, 4, because when you swing this pair down, it leaves 4 dots over here. We put the nitrogen dots up top, and then we're going to bring these remaining electrons here. So there's one valid structure. And then the second structure would have your double bonds on the other oxygen. Okay. Resonance with your polyatomic ions. The carbonate ion has 3 valid resonance structures. Notice you have a double bond that can be on the top oxygen, one on the bottom left, and then one on the bottom right. So you would need to draw all 3 structures. Acetate ion. Acetate has 2 valid resonance structures. Notice the resonance is occurring here between your carbon on the end and the oxygens. That is our lesson for resonance. The next lesson we'll pick up with formal charge.